Morning, everyone. Thank you for pressing recording. Yeah, I was gonna, good morning, afternoon, evening, or night, wherever you are. Before I pass on to introduce to our keynote speaker, please be aware that the session is recorded and that you are welcome to post your questions on the Q&A feature. And now, moving on, it is my great honor to welcome you all to this first keynote of this International Day of Women in Statistics and Data Science 2024, and to introduce you to our keynote speaker, Professor Kerrie Mengersen. Professor Kerrie Mengersen is a distinguished professor of statistics and director of the Centre for Data Science at the Queensland University of Technology in Brisbane, Queensland, Australia. Her primary research interests are in Bayesian statistics and the application in environment, health and society. And Kerrie is an elected member of the Australian Academy of Science and the Academy of the Social Sciences of Australia, and also a current vice president on the International Society of Australia. Her talk's title is Modern Bayesian Statistical Science, Challenges and Opportunities. And without further ado, I'll pass it over to Professor Mengersen. Thank you very much for joining us.
Thank you very much, Althea, for that introduction. And thank you very much for the honour of being able to speak at this meeting. It's indeed a great day for the international statistics. So to all the women statisticians out there, all the women data scientists, and all the women scientists across the world, kudos to you. And I think it's fantastic, all the work that we are collectively doing. I'd like to just share my screen and then continue with my presentation. Just bear with me for a minute. I seem to be...
We can see question.
Okay, let me see. Can you see my screen now?
Yes, perfect.
It's just
That's
a bit
great.
slow.
Thank you.
Okay, good. All right. So I'd like to talk about Bayesian statistical science challenges and opportunities. And I'm hoping, Althea, you'll keep me to time. Yes. Good. All right. So I'd like to start just with a question to everybody who's listening. And the question is, if I toss a coin 10 times, then what is the probability of a head in the next toss? And this has a follow-on questions. So, for example, if there are no deaths in 100 heart operations in a hospital, what's the underlying death rate from heart surgery? And so I worked on a project looking at risk from death of heart surgery. And so this is a real question that has come up in my work. Another question that is a real question that's come up in my work is if there are no detections of an exotic pest in 1,000 samples as part of a large biosecurity project, can I declare that the pest is extinct? So this project was with Chevron on an island off Western Australia. It's a conservation island. Chevron was looking to put on to implement a large gas works there. And the demand from the government was that they needed to make sure that they didn't introduce exotic pests with 80% confidence. And so the question was, what does that mean, 80% confidence? And how can we set up a biosecurity program that would actually comply with the government demands? And so this was a real question as well. So if we look at these questions, then these involve probability and they involve data. And they also involve some sort of understanding of like what can we predict based on the data that we've seen. But of course, we don't just have the data. We also have some knowledge about the process or the system. So does your answer change about the probability of a head if you know it's a biased coin? What if you know about the probability of death from heart surgery? Does this change based on, for example, if you know something about other hospital rates or hospital rates or rates for this hospital in the past? Or in particular, what about for an individual instead of the hospital as a whole? What can we say about those probabilities? And similarly, about biosecurity risk, what if we consider the impact of climate change? And so the biological or ecological niches that we've been typically searching may not be appropriate in the context of climate change. So these kinds of questions then provide a context for the system or the process, and we need to be able to take this into account. And so what we think about then is, in a Bayesian statistical science framework, we would think about this as our current knowledge. So what do we understand about the system or the risk or the relationship or the prediction that we want to make? What do we understand about that now? So what's our current knowledge? And we would cast that as a prior or prior information. And then we combine that with the data. And the data is expressed through a model and then formalized through a likelihood, which is the probability of the data given the model and the model parameters. And then based on the combination then of our current knowledge and our data, we then update our knowledge and we get this posterior understanding of the system. So we go from our current knowledge, we combine data, and then we get an updated knowledge. And then we can iterate around that system so that our updated knowledge becomes our current knowledge, we can get more data, and then we can update that information again. And so that, of course, is our natural process of learning. In fact, that's the underpinning of artificial intelligence, and it comes through this idea of Bayesian statistics. And so if we think of a sort of history of Bayesian statistics then, what we get is this sort of potted history, if you like, where we had in 1763, Bayes formulated this idea of probability, and I'll come back to that, and that was then published by another person, but it was Bayes' work, and Laplace at the same time was coming up with similar ideas around the idea of probability theory and, in fact, inverse probability. So this probability of an outcome given the data. Now, if we think about this probability of an outcome given the data, then the parts that we need to this are the data given the outcome is in the middle, and then we also give the data given the model and also the prior information. And so the difficulty with this then was the nature of priors. And so what do we understand about priors, and how can we formulate an objective prior, for example? And there was a lot of debate around this, and also then the computational issues involved in implementing the Bayesian framework. And so while this discussion was happening, and while there were a lot of debates about this approach that Bayes and Laplace had put forward, Fisher and Neyman at the time were proposing a likelihood-based approach. So just focusing on that blue circle there, the likelihood, and not including any prior information. And so this then led to the sort of the maximum likelihood approach that in the sort of dotted line, if you like, really sort of took off. And Fisher and Neyman were very strong proponents of this likelihood-based, this frequentist approach. Meanwhile, there was a lot of work done by Jeffries and others to overcome or to formulate priors and to understand priors and to formalize them in terms of an objective prior that could be used in Bayesian computation and Bayesian modeling. Gieman and Gieman were some of the early proponents of using developing computational methods like Markov chain Monte Carlo approaches that enabled us to do the Bayesian computation. So taking a very complex model and a complex Bayesian formulation and being able to break it down so that then the computation became much easier. And these sort of methods then really started to allow us to do modern Bayesian analysis. Those methods were then extended by people like Gelfand and Smith and formalized into models. So we had all of the architecture now. We had the priors, we have the models, we also have the computation that really enabled us to accelerate Bayesian modeling. And today's Bayesians now in the 2000s and now in 2024 build on all of that foundation. So that's our sort of history of Bayesian statistical science. But we still have challenges and opportunities. And surprisingly, or perhaps not surprisingly, they relate to the fundamental questions that we have. What are the challenges and opportunities with respect to priors? And in fact, a challenge and opportunity is really about the nature of probability. And I'll just very briefly touch on that as well. There's also the challenges and opportunities related to computation, which was a sticking point at the beginning of the Bayesian timeframe, and is also a sticking point or something that is still a great area of research now. And then there are putting all the bits together to look at how we can do Bayesian analysis for real world problems. And so I'd like to talk about just a few of those exemplar challenges. So I'm going to start first with like the question of what is probability and touch very briefly on this issue. So this was really a probability war in the like over hundreds of years. So in the late 1700s, we had Bayes and Laplace thinking about probability as a measure of degree of belief. So it was really a personal expression of how sure you were about or how much you believed a particular outcome. It was a subjective probability. Then in the early 1800s, or mid-1800s, was really a proponent of the scientific perspective on probability. So this is a frequency of a particular outcome in a potentially unlimited series of possible events. So a very scientific perspective on probability and very different from the subjective probability approach. Jeffreys and De Finetti in the 1900s, so again, came back to this idea of a degree of reasonable belief. And so there are these debates, if you like, or different kinds of definitions of what probability is. And indeed, today we have a number of different ways that we think about probability. And I've listed just some of the different approaches that people will talk about in the context of probability. I won't dwell on this, but I just wanted to flag that these challenges and potential opportunities for research still pertain to the very essence of statistics and statistical science, and indeed Bayesian statistics. The second issue was the challenges and opportunities around priors. And so these are still questions that are asked today. What is an objective prior? An objective prior from Bayes' approach and Bayes and Laplace was really around trying to come up with a principle of indifference. I want to put a prior on either the parameter itself of interest or on the predictions that is going to reflect sort of an indifference from the author of the model. And so this was either a uniform prior, or if we have these extreme questions, as I asked at the beginning, like seeing 0 successes out of a certain number of trials, then there are different kinds of priors that have been suggested for this. And work even today, as you can see here from the first reference from Frank Tal, really tries to, again, think about what kinds of priors really reflect this objective thinking. In a more complex model setup, we can think about mixture models. And mixture models are where we have underlying subgroups in a population, and so they can be modeled as the population itself is a mixture of different components or different subgroups. And when we're in that situation, the question is, how many subgroups do we have? And so the prior actually plays a very large part. The prior on, the weights that we put on the different subgroups plays a very large role in whether we can automatically determine how many subgroups we might have in a mixture distribution. And so these priors are objective priors, either from the case of these extreme situations, as I described in the beginning, or in the case of these more complex models, like mixture models. There are also not objective priors, but semi-informative priors. And I've just flagged one here, for example, where instead of looking at an objective prior per se, we say we have some knowledge of a system and of what the priors might be. So we understand that the parameter of interest is within a certain range, and it would be really foolish if it was outside that range. Or the predictions would be in this range, but it would be really strange to see them outside of that range. So what would be tenable statistics for future data? What would be untenable statistics for future data? And deriving from that, what the priors would be that would allow us to entertain the kind of predictions that we would make under those priors. And if we can do that, then we can sort of constrain our set of priors to have properties that we would believe in. And then that's sort of called semi-informative priors. And so there's some really nice work going in this idea of trying to come up with priors that are not completely objective, but have some very general or very light information in them, but the data still has a very strong speaking voice in the analysis. And then we go to a case where we have priors that are very strong. So they can be very subjective priors, for example. So these are priors that may come from our experts or may come from our they can come from our experts or they can come from prior literature and so on. So these subjective priors, especially from around eliciting information from experts that we can then use as priors in models. And so this work's been going on for nigh on 20 years where we've been doing this, and it's been very interesting to see how we can actually extract information from an expert and then formulate it as a prior for integration with data in a Bayesian approach, and this is very effective as well. Now, the subjective priors can also be extracted from citizen science, so where we have many members of the public who can provide information, and we're really trying to build then on this volume of information that we have, recognising that some members of the public will be better at providing information than others. And we see a whole lot of citizen science projects where this kind of new data in citizen science is something that statisticians and Bayesian statisticians trying to deal with so that we can increase the trust in this kind of citizen science data. And people in this area who I'm working with are Julie Versaloni and the team there, and I'll talk a little bit about the project on Virtual Reef Diver, and also Edgar Santos Fernandez, who's working similar projects and looking at increasing trust in these new data sources. And so we can go from this very objective view of priors right through to the very subjective view of priors. And the picture that I've got there actually that is up there is we've also been experimenting with using virtual reality to put people in the picture, if you like, or in the scene, and then eliciting information from them and then incorporating that in our models. Now, I'd like to talk a little bit about computation, and again, just touch on this. But right from early days of modern Bayesian statistics, the question of the kind of algorithms that we have, and these are Markov chain Monte Carlo algorithms, names of particular types of MCMC algorithms are Hastings and Metropolis algorithms. And these are empirical methods. So we basically sample from distributions, conditional distributions that give us the whole posterior distribution, and we need to make sure that they converge. And so what are the sort of theoretical properties of these kinds of computational methods? And this was early work in 1996 with Richard Tweedy, but then also looking at extensions of that for Bayesian computation for different kinds of likelihood. So instead of setting up a very formal distribution for a likelihood, we can have empirical likelihood. So likelihood that's based on the data or aspects of the data. And then also for Bayesian computation, instead of bringing together all of the data, we might be thinking about instead leaving the data where they are and then analysing the data in the cloud. And so just talking about this federated learning approach, which is very popular, but also like just starting to emerge as a real tool that we might use in practice. The federated learning approach says instead of combining all of the data, we would leave the local data in the locations, and then we have a local models, and we also have a global model that takes information that we need to build the global model from the local data sources without actually seeing the data themselves. So the data themselves are not shared. The data, it's just extracts of the data or summaries of the data or parts of the calculation that we might need to develop the full model. And it may be an iterative approach in going back and forward from the full model to the local models as well, or the local data. And so there's a lot of utility in this because we are leaving the data custodians to manage the data. We are respecting privacy of the data. And so we overcome many, many concerns that we have in current analysis. And so these kinds of computational methods are really exciting as well. So there's a lot of work in Bayesian computation that was one of the sticking points from the 1700s that we're still learning about doing well today. Right, so I'm just going to talk a little bit about some exemplar challenges and bring these different approach or different concepts together. So bringing together the concepts of priors, bringing together the concepts of models and also of computation. And the first one's really about this idea of eliciting information and combining it with our data, but in a different way in this one. So this is around combining stories and data. The second example will be around virtual reef diver, which is, again, using citizen science data to combine with our observed data, and also then modelling complex systems. So we'll start with the first one, which is Healing Country. And this is a project that is led by Veronica Matthews, who's a health researcher, associate professor, an Indigenous associate professor that I'm working with on a project of combining Indigenous community stories, so stories from our First Nations people with our Western data, so data that we've collected from monitoring stations for long periods of time. And so there's a real interest in being able to bring together the knowledges from the Indigenous communities around this particular project is around their stories of coping with environmental change and the impact of the environment on their health and social well-being and well-being. And then thinking about the long-term monitoring of climate that we have and how we might combine these as well. So the kinds of themes that come out from the discussions with the communities, the Indigenous communities, are around health impacts, but also seeing in the climate a changing climate, more rain or less rain. It's hotter or it's colder or it's more variable. A lot of comments around vulnerability of the people to the health and to the changing climate, and also related to that, then the loss of biodiversity and the change in the ecosystems as well. So a related project that feeds into this that we have been involved in is a project on Ausen Health, and the lead investigator in this, or co-lead of this, is Aidan Price, and it's with a consortium of researchers and a consortium of organisations. Ausen Health is Australia's first national digital environmental health decision support platform. There are 8 collaborating organisations, 183 environmental health variables that we've collected so far, and some vulnerability indices that we've developed as well. And the idea here is to bring together the environmental data and the health data at scale. So this is all the Western data, but across Australia. And so it would be looking at heat, climate change, looking at air quality, and different ways of providing this information. We have a new project, a new funding for this project, so it will be continuing for another 2 years. And in that time, then combining it with the Healing Country project. But in the AusN Health project, for example, when we look at heat and looking at the visualization of this, we can have a map, then a choropleth map, which shows what's happening across Australia with respect to extreme heat. And for any particular region in the map, we can see where it lies in terms of the comparison with the other regions across Australia. So at this particular scale, if we're at SA2 scale in Australia, for example, there's about 2,000 SA2s across Australia. SA3s, there's about 200 of them. And so that's the kind of numbers of regions that we are looking to provide information for, data for, and also to model that. And so in the Healing Country project, we have 3 main sites. So the AusN Health project would feed into the Healing Country project. There are 3 main sites, one in northern New South Wales, one in Warramungu in Northern Territory, and one in Western Australia in Perth here. That's the Whadjuk Noongar site here. So we have Bundjalung, Warramungu, and Whadjuk Noongar. So these are quite, Bundjalung and Whadjuk Noongar are either sides of the country, quite temperate climates, and we get a very remote, arid climate here in Warramungu country. So if we're looking at what the Western data tell us about this, then we can see we've just pulled out then the changing climate. So this is like Bundjalung country here, and you can see the average temperature, and the average temperature really is rising. So the sorts of themes that we're hearing from the local community can be supported by this kind of data. So this is rising for Bundjalung. Similarly, we can see this for Whadjuk Noongar as a large increase. So this is the 2 temperate sites. And then for Warramungu, which is already quite hot, you can see here that there's a change in the variability of the temperature as well. So these sorts of, this kind of data then can be combined with the stories of the community. We can also look at projections. And so for the 3 sites, we can take the IPCC projections and try to understand what these particular sites will look like into the future. As you see, there's quite, goes from relatively conservative estimates through to quite concerning estimates for the average temperature. Another way of looking at temperature is to see it like this kind of visualization. So for a particular site here, over time, you can see the years changing here, and you can see for each of the days of the year, the temperature. So red is maximum temperature, is high temperature. So this is all maximum temperature. This is high temperature, and here is our the low temperatures here. And so that's for Bundjalung country. Katie Buckhorn developed these visualizations. Thanks, Katie. And for Warramungu, this is what we also see here. And you can, again, see this really big change over time. And then for Whadjuk Noongar, you can see also the change over time. So you see this change in the amount of red and the amount of blue. So you're starting to see, the variability and also the increase in the temperature as different visualizations. And so this then can be, in AusN Health, can be incorporated. So we have the data per se, we have AusN Health time series, what's happening over time with heat indicators, not just temperature. And we can also look at that in terms of, for example, changes in the number of fire risk days. So this is a change from over the last few decades And what you see here is a lot of red, which means that there's a lot more at-risk days in fire risk. Now, obviously, it's not just temperature, it's also rainfall. So just skipping through these, we can also give pictures of rainfall and what's happening with rainfall in these different areas. And similarly with air quality. I'll just pause on this one for air quality. You can see the big spike here for Bundjalung country. And if any of you just pause for a minute and wonder what that is, that's actually from a very large fire, fires in the region. And so we see that reflected in the data, and we also hear that in the stories from the communities. So we can create indices then, so vulnerability indices based on the data for the different areas. And for heat then, these vulnerability indexes for one place, this is Warramungu country, and what we see here, these are the sub-indices, so adaptive capacity, exposure and sensitivity. And for this particular region, it's really the exposure that's driving the vulnerability index here. So our data is telling us this information that's very useful to think about how we actually combine it with our storytelling. So then what we're doing is having storytelling with the different groups. This is a story with one of the community groups, and then we need to then be thinking about how we combine these stories with our data, and that's the chapter for next time. But what we can do is to think about how we do that comparison, or sorry, that combination through another project, and this is Virtual Reef Diver. So Virtual Reef Diver looks at a project for the Great Barrier Reef. And the Great Barrier Reef is 2,300 kilometres long, so it's very long. It has great monitoring by the Australian Institute for Marine Sciences and other groups, long-term monitoring over 20 years, but it's at certain sites. And so what happens in between those sites? So what we've done is create a virtual reef and said, well, any number of divers out there with their cameras can, or any other studies that are taking underwater images, can geotag their photos to this virtual reef. And then we can take those photos and ask people from around the world to annotate those photos for coral, algae, sand, and we can then extract those annotations at the back end from the website, and we can combine that citizen science data with our observed data at the specific locations. And in doing that, then we can fill in the gaps. So we have our long-term monitoring data and our citizen science data that we're then combining. So we have our map here. We ask the divers to take photos, or the studies that are taking underwater imagery to tag their photos then to the virtual reef. We ask people from around the world in their living rooms to annotate these images for coral. We then take that information out the back end and we combine it with the data. So it's more than just a website. We ingest the images, we have the coral classification, we extract the information, we build a model and fit predictive models, and then we can visualize and download Great Barrier Reef wide predictive maps. So of course this feeds into our SDGs, our Sustainable Development Goals, and also the strategies for the Great Barrier Reef. We can use this then to estimate we can model these data, and this is work of Edgar Santos Fernandez that you saw before, and others, and Julie Versaloni, to estimate the ability of the citizen scientists. So we can identify then the citizen scientists that are very good and accurate, and those that need more training. We can also take into account or understand the difficulties of the categories. So how difficult is it to annotate or to identify algae or hard or soft coral or sand or other features in the images? And if we look at, well, what's the benefit of including this citizen science data? If we just look at the long-term monitoring alone, we have our observed versus our predictions. But if we add the citizen science data, then we get much better predictions. And so taking these data and being able to, the citizen science data, being able to increase the trust in those data by modeling those data per se, and then being able to combine it with our data, our observed data, our long-term monitoring data, then allows us to have much better predictions of the health of the reef. So what have we learned by doing this? So some of the insights: improve predictions of coral cover, and we also get the uncertainty around that. There are heat waves and cyclones that have heat waves and cyclones have a substantial negative effect on the proportion of hard corals, and no-take marine reserves and middle shelf reefs tend to have substantially higher proportions of coral. And so this is work of Julie Versaloni in pulling out these insights, and her colleagues. And this work then has really laid a foundation for some of the extensions that have been are in progress by the Australian Institute for Marine Sciences. So Australian Institute for Marine Sciences is doing some great work on a project called Reef Cloud, which is taking or trying to use citizen science and automated annotation of images in the Pacific. So for many of the Pacific Island countries that have coral reefs and are really being subjected to climate change. So if we look then at this automated imagery that we can do through analysis or annotation of images that we can do through machine learning methods, and also the citizen science data, we can ask, well, why would we do citizen science analysis and annotations when we can do the automated annotations? What we find is that there is some sort of boundary where the citizen scientists can do as well as or better than the automated machine learning methods. And in fact, in some cases, some of the citizens can do much better. So if we can identify those citizens, then we can really start to provide a much more nuanced and accurate prediction of the health of the reef. So the last project that I would like to touch on is one on modelling complex systems. And this is work from Paul Wu and led by Paul Wu and Sandra Johnson. And so in about, it's work that's been going on for about 15 years, I've been involved in developing these Bayesian networks. And I'll talk about the Lingbia project here and touch on the more recent work that Paul has been doing as well. So this project on Lingbia, which is a cyanobacteria that sort of fouls our waterways, and this is Sandra Johnson pictured here. A lot of work on developing a complex system model, a Bayesian network approach to this. So a different kind of Bayesian modelling that we can use for these complex systems. Paul Wu and co-authors has been working for a number of years on looking at dynamic Bayesian networks, and this is for marine ecosystem resilience, and in particular the impact of dredging on seagrass. And I'll also put a call out for Paula Sabenko-Haytham, who has just finished her PhD on this topic of using dynamic Bayesian models for seagrass, and has just got a postdoc in France. So she's over there working on the same topic. So congratulations to her. So almost everything is a complex system, whatever we think to model. There's nuances in the processes, and there's issues that we need to take into account when trying to make predictions or understand relationships. And so there's many different factors that are involved, and often if pulling out just one factor and trying to understand it is useful, but it's also more useful if we think of what other factors might be involved. But when we start to do that for ecosystems, we start to do that for biosecurity, or we start to do that for health risks, we start to do that for conservation, then we start to see the complexity of these kinds of models that we want to build. So instead of looking at a simple likelihood and a simple model, we really have to start to think about how can we put together various types of data from different sources, and also various types of variables or factors that would impact on an outcome. And one of the ways that we find very effective to do this is through a Bayesian network. So a Bayesian network can be considered as a directed acyclic graph. We can have a graphical model where we have an outcome. What are the factors that impact on the outcome? What are the factors that impact on those factors? What are the factors that impact on those factors, and so on? So each of the factors then is denoted by a node here, which is the green circles, and the relationships are by the directed arrows. And so what we want to do then is to think about this kind of model, which this kind of model then allows us to have an outcome of interest and maybe multiple outcomes, and then the factors that affect those that outcome. And then those factors can be quantified by different types of data. And so we do this then by probabilistically quantifying the network using data, literature, model outputs, expert judgment, and so on. So if we just look at the nodes in the circle here, we have G is going to be dependent on factors E and F. And so we model the probability of G having a particular outcome, in this case, whether it's normal or high, and that's going to be dependent on the state of E and F. And so this can be quantified using different types of information and provides these conditional probability tables. So we go through the model, we quantify it like this, and then we can run those probability tables through the model to come up with the overall outcome. So we can extend this then to object-oriented Bayesian networks, dynamic Bayesian networks, and also decision networks. And so many variations on this kind of basic theme. We use these kinds of models, bringing together disparate scientific information, creating this conceptual map of the scientific drivers, which is usually very useful in its own right, but then to quantify that with data and other information. And we can do that. Once we've got that, then we can identify the key drivers. What are the drivers that are really affecting the outcome given all of the other variables in the system? Scenarios of change. What if we had a particular scenario in those factors? How would that impact on the outcome? And understand then the impact of management and policy decisions. So this kind of Bayesian network is a really useful way of integrating diverse sources of information and diverse factors that might impact on an outcome. And so an example of this is Bayesian network modeling of Limbia. So said this is a cyanobacteria. It's like like toxic to fish. Pain can often be harmful to humans, and then also comes up on the beaches and creates a mess for the local councils and for tourism. So the network that we developed was looking at the bloom initiation. Is going to be impacted by the dissolved elements, and then we also have the sediment, we have temperature, and so on. And each of those then are impacted by other factors, and each one of these nodes then contains a subnetwork in behind it. So once we quantify the whole network, then we can say, all right, well, what if we go and change the point sources? How would that then change bloom initiation given everything else in the model? And if we do this, then we can see what are the most influential factors. In this case here, we saw the available nutrient pool was most important, and then you can see the other factors there. And this available nutrient pool is something that we can do something about. And so management actions can be taken based on this analysis here. So if we actually work on available nutrients, we can take that back to a management model and go, okay, how do we actually change the available nutrients in the catchment area? And so that might be through changes to agriculture or changes to sewage systems and so on. That then, the results of that feed back into the science model, which then changes the bloom initiation. And so we get this integration of a management model and a science model through this kind of Bayesian network. Now, the work that Paul Wu has done is to take this further to look at dynamic Bayesian networks, so that's networks over time, and he was looking for ecological windows for dredging to reduce the impact on seagrass. And so different types of ecological windows, different types of dredging regimes, and looking at how that might impact on the different species of seagrass. And what he found was that resilience is dynamic in space and time. That's seagrass resilience. This ecological windows, if we get it right, we can actually have a 4-fold reduction in recovery time of the seagrass due to dredging, and a 35% reduction in extinction risk, which means that these kinds of models can be used then to identify appropriate dredging regimes that can have a dramatic effect on the sustainability of the seagrass systems. And this is really important for the very many areas across the world that have this kind of dredging regimes and seagrass as well. Now, of course, we have a lot of opportunities in Bayesian statistical science. Modern statistical science brings together maths, stats, diverse data, new deep models, new computational methods, software products, complex challenges, a whole lot of questions about AI and ethics, which statisticians should be really involved in. And all of these then require theory, models, priors, inference, and algorithms. Modern statistical science, then embedded in that is the Bayesian statistical science, which also encompasses all of these features and all of these challenges and opportunities. And so what we see then is what's next, and my argument would be that engaging in data science, having Bayesian statistical science really closely connected to computer science, information science, AI, data engineering, and of course the domain sciences, really provides a rich opportunity for us to grow our methodology, to grow our tools, and to grow the way that we might be able to really tackle some of these really large challenges that are facing our world today. So here at QUT, we have a Centre for Data Science, which brings together these groups for across the university from the different disciplines, and then seeks to increase our research in the whole area of data science for impact. And also we have then created an Australian Data Science Network. So this then links the different centres for data science across the country so that we can raise profile, increase opportunities, increase communication, and so on. We're a big country, smallish population, lots of data science centres emerging, and this data science network allows us then to have the communication between those different centres. So we're having our conference soon in Perth. You're all very welcome to attend. It will be in December, and so you can search for the Australian Data Science Network and find out more about that, and of course find out more about our Centre for Data Science and the work we do as well. And on that note, I will finish. Thank you.
Thank you ever so much, Kerrie. That was a fascinating talk. And I must say it was great to see that the history of Bayesian statistics is now full of women, moving from all those men in the first plot to all those women in your project. That was particularly fascinating, and looking at the ways in which you are integrating data from very different sources. If there's any questions at the moment, I have one actually around the Healing the Country project. I found that fascinating, and I was wondering, how are the communities finding the project is helping them? What was their main motivations to getting involved?
Yeah, thank you, Althea, for that. The project is very closely coordinated and co-designed with the different communities. So they are very aware of the impacts of the impact of climate changes. So for example, in the middle of Australia, it is very hot, and they need housing that is appropriate for that kind of temperatures, those kinds of temperatures. And so having the stories that are told and also then the data to support those stories, and also thinking about the interesting thing for me is not just having the data as the backdrop for their stories. That's very useful, because that's sort of two lots of evidence, if you like, and they can take that to government agencies and so on. But also for us to think about how does their knowledge actually impact on our data and our understanding of projections and understanding of our understanding of the Western data. So the way that I think about this, and it's a work in progress, and I'll be very interested in others who might also be working in this space. But again, one of the sort of starting questions I had was, if we know something about a hospital, for example, what does that mean for an individual? So if we thought about that kind of question in the context of the Healing Country Project, our data tell us about a site, so here's the temperature, and temperature's rising, and we have this projection in temperature, projected rise in temperature. But we know that there's many individuals in that area that are going to have different responses to rising temperature, and because of different infrastructure and because of their own socio-demographics. And so we need to, so how can we then use their stories to actually build more accurate individual trajectories? So taking our Western data and the stories then to almost modify our Western data for their individual trajectories. So that's the kind of thing that we're looking to do. It's early days in that kind of merger of the projects, the merger of the data sources. But I think the Bayesian approach is a way that we might be able to do it.
Fantastic. And do you think Bayesian approaches are easier, allow for easier ways to communicate with different audiences, like in this case, these communities, to explain to them that you are using their previous knowledge is being included in the models? Does that facilitate the conversation?
I think it's useful to be able to acknowledge that there is existing knowledge and information, and that there are ways to combine that with the different sources of data can be combined, and a Bayesian framework can do that. And whatever we call that, I mean, the architecture is really one where you're just having this continual updating. So we have a current understanding, we bring in data, and then we update that understanding. And I think even for all of us, when we're looking, even if it's an objective study, what we would do is to do a scientific study, for example, and then we bring our own interpretation. Do those results reasonable? What would I do? What's going to be if we're trying to make a decision on the basis of those data, we typically would take the data and the results of that study, and then overlay our understanding of the systems or prior data or what we know about the individual, and then make a decision on the basis of that. So we are implicitly doing this sort of Bayesian approach. What we're doing in the Bayesian framework is formalizing that kind of information that we are going to overlay on the data.
Fantastic. And just one final question, I suppose. Is Bayesian statistics a solution to the potentially computational cost impacts on sustainability around big data, AI, and so on? Does Bayesian fix some of these problems? Do Bayesian approaches?
Yeah. What I see is there's a number of ways of thinking about that. One is that we can build submodels, and then and so through those sort of submodels, and then combining those, so we can think about as a model structure that allows us to combine those different data sources, and also there are fast computational methods for dealing with the sort of the big data, if you like. And so some of those are emerging. That's really great to see. But also we can think about intelligent data collection. So, for example, if we do have a lot of data, and we have a large data set, for example, if we want to ask a particular question, we don't need to analyze all of the data. And so that might actually allow us to come up with much more simple models, if you like, or simple analyses, because we can take the data that we actually need to answer the question. And so in a little while ago, we thought about this from sort of intelligent data collection. So if you have a question you want to ask and you have a design for that question, you build a design. So what would be an optimal experimental or survey design? And then you lay that design out over your data and you collect the observations corresponding to the design points. And then you can do the analysis of those. So that, and if you don't see data corresponding to the design points, then you know that you're missing something. So it may well actually be an indicator of bias in your data or a gap in your data that you wouldn't have been aware of before. But the advantage of that is that then you're just lifting out the data that's corresponding to the design, that's corresponding to the question that you want to ask, or allowing you to answer the question you want to ask, and you can replicate that as well. So there's a lot of advantages in doing this kind of intelligent data collection, and this kind of approach can allow you to do it.
Fantastic. Yes, I certainly love that idea and that concept, and I'm going to use that term, intelligent data collection, for sure. So, yes, it's only left for me to thank you again very much for a fascinating talk. I think you've raised very important questions for the profession as a whole as well, and for the Bayesian statistics field in particular. So, thank you again for celebrating this day with us, and we hope to see you again next year.
Thank you very much, and thank you again for the opportunity to participate in this. It's such a great event, and thank you for being such a great moderator. Thanks,
Fantastic. Thank you. It's our honor. Bye. A reminder to the audience that we are now gonna move into different rooms. So if you are moving into other, please make sure to take your session so you can move to the appropriate room. Thank you.